Good morning, Professor. I am Anveer Singh Sandhu, and today I'm going to be presenting one of the most essential, important parts of software engineering called unit testing. And throughout this presentation, I'll explain what software testing is and why unit testing specifically is the foundation of the testing process, and how you can use tools like JUnit, Mockito, and they will help us write reliable and maintainable and testable code. And I'll be using the practices from experts like Martin Fowler to explain how to do some of these things, and clean code principles, and test-driven development. And by the end of my presentation, should have strong understanding of what, not just what unit testing is, but why it matters and how to write good tests and fit them into real software development. Introduction to software testing. So, what exactly is software testing? What a software tester would do is evaluate if a software is meeting the requirements and behaving the way it is supposed to. And they would do this by putting in as many real-world conditions as possible. And at the end, it will identify if there's any defects, any bugs, or any missing requirements before they actually release the software. There are some functional requirements and some non-functional requirements that are the goals of software testing. So the functional requirement is, of course, to check if it does what it's supposed to do and behaving the way it's expected. And the non-functional requirements are the performance, the reliability, and the scalability of the software. And identifying these reduces the risk associated with the system. And the sooner these defects are found, it reduces the cost and the risk posed to the company. The later a bug is found, if it's found like after release, then it costs the company a lot to fix, because there may be like many previous mistakes made by it, and you have to go back and fix all of them. So it supports quality assurance and system reliability. Although there are so many benefits to software testing, and it seems like it may just like fix all your problems with the code, but there are many things that testing cannot do. Testing does show the presence of bugs, and it may show like where the bugs are, but it cannot show their absence. What this means is, if you run the test and they come back clean, it doesn't mean necessarily that there's no bugs at all, because there will always be some unexpected user behavior and some special cases that are not run during the tests. So it can't prove that the software is completely flawless. This is because even if it comes back with no bugs, the coder could still have bad architecture, some like bad design, and poor coding practices. So it might run the tests properly, but these poor architectures would make the code messy and lead to unexpected issues outside of the testing environment. It also doesn't guarantee user satisfaction, because a product might technically work perfectly, but it can be confusing and unpleasant for the user to use. The 4 levels of software testing are unit testing, integration testing, system testing, and acceptance testing. Unit testing is the smallest component code that is tested in isolation. This helps ensure that each part of the code works correctly on its own. Next is integration testing, which checks how different components work together. Even if individual units are correct, they can still fail when combined. So this level is essential for finding interface issues or data mismatches. Then we have system testing, which is where we test the entire application as one complete system. This includes looking at functionality, performance, security, and other real-world conditions to make sure everything meets the requirements. And the last level is acceptance testing. This is the last checkpoint before you release the product. So this is where you have actual users or stakeholders validate that the system meets the business needs. And these 4 levels come together like a pyramid, for example, with the base being the unit testing, and building your way up to the final product. So why should we focus on unit testing out of all of these levels of testing? It is because unit testing forms the base of the pyramid, and it is necessary for being able to do the other stages. And it is one of the most important because it catches bugs at the earliest and the cheapest stage, because unit testing is the fastest form of testing and provides instant feedback, and it makes sure that the code works in isolation first before you can make sure that it works with the rest of the code, and it supports clean, maintainable code. Unit tests also help ensure the code is well structured and ensure that these small mistakes don't grow into bigger problems later in the system by catching them as early as possible. So to begin, what exactly is a unit? A unit is a function, a method, or a class, depending on the language, and is the smallest testable code. A unit should be independently testable, and this is very important because to isolate the code that you're testing, it has to not be dependent on any other code because you're not using it for the test. And what makes a good, easily testable unit is when it has clear inputs and outputs, it makes the unit testability much easier. Now next are some characteristics of these unit tests. So first of all, when we talk about a high quality unit test, it must be fast. It should run in milliseconds because developers need to run them constantly, and slow tests make people avoid testing, which defeats the whole purpose. Next, the unit test must be isolated, of course, because it shouldn't depend on databases, networks, file systems, or any external environment. If the test relies on something outside the code itself, it's no longer a true unit test. Isolation ensures that failures actually point to a problem in the code, not in some external system. Another important trait is that unit tests must be deterministic. The same input should always produce the same output, and the result should never be dependent on some randomness or timing. So it should pass every single time that you run the test under that same condition. So it must be repeatable. And the best way to run these tests is to have them automated so they can run as fast as possible and can be incredibly useful for maintaining code quality. Next is the introduction to JUnit. JUnit is the standard Java testing framework. It uses annotations like @test for readability, and it supports structured test organization and automation. So it allows developers to create automated, repeatable, and isolated unit tests. It's part of the XUnit family, and it's widely used for test-driven development, TDD, regression testing, and improved software quality. With JUnit, we can verify the behavior of individual methods, classes, units of code using simple annotations like @test, @before each, @after each, @before all, and after all. to manage the test setup and teardown. It provides a rich assertion such as assert equal, assert true, assert false, assert throws, and assert not null, which help validate expected outcomes. And since JUnit tests are fast, lightweight, and fully automated, they're perfect for continuous testing, refactoring, and enforcing clean code principles. Overall, JUnit is essential for building reliable, maintainable code for Java applications and ensuring that each unit behaves exactly as expected. Now here is some further explanation on the JUnit assertions. The assert equals checks equally of expected and actual values that you get, and assert true or assert false, they validate Boolean expressions, and assert throws validates correct exception handling when the user does something unexpected and you have to go to the exception. And these assertions communicate expected behavior clearly versus what the actual values of the code are. Introduction to Mockito. Mockito is a Java mocking framework used alongside JUnit to create mock objects, stub behavior, and fully isolate units of code. Because many units of code, you can't just create them in a way to be dependent from APIs, services, and databases. But in order to do unit testing, you have to make sure that they're isolated from them. But how do you test a code that cannot work isolatedly? So that's why we use Mockito to create mock objects and stub behavior to test these units. Using Mockito, we can perform mocking, stubbing, and verification. For example, we can stub behavior using when, then return, or then throw, allowing us to stimulate specific conditions or errors. Mockito also provides argument matchers such as any, EQ, and any string to make tests more flexible. With verify, we can confirm interaction patterns like whether a method was called, how many times, and with what arguments. It also supports spy objects, void method stubbing, and behavior-driven testing using the given, when, then syntax. It integrates perfectly with dependency, injection, Maven, Gradle, and CI/CD pipelines, which makes it essential for building maintainable, scalable, and high-quality Java application. Overall, Mockito is a critical tool for writing clean, isolated, and professional unit tests. When should you use mocks? We use mocks in unit testing because we want to isolate the system under the test and avoid relying on real external dependencies, because those dependencies can have bugs with them themselves, and then you wouldn't know where the bug is coming from and you can't pinpoint it, which defeats the purpose of a unit test. Only once the units are running well independently, then you can move on to seeing how well they fit together. Mocks are especially important when dealing with slow components like databases, file systems, and remote APIs, because unit tests need to stay fast, deterministic, and repeatable. They're also essential when a real dependency is unavailable, such as a third-party service or incomplete modules or external systems that aren't ready to be tested yet. Another major reason to use mock is interaction verification. With verify, we can confirm whether a method was called, how many times it was called, with what arguments, and which is key for collaboration testing. Overall, mocks support true isolation, dependency injection, test-driven development, TDD, and high-quality, maintainable unit tests. And you should use mocks when dependency is non-deterministic, meaning it is random or time-based. You should use mocks versus stubs, according to Martin Fowler. Stubs provide canned responses, which are used for indirect inputs, and while mocks, they verify behavior by checking method calls. According to Martin Fowler, classic article on test doubles, mocks and stubs serve different purposes in unit testing. A stub is an object that with the canned responses to method calls. Stubs are used to control the indirect inputs of the system under test, making the test deterministic, consistent, and isolated from real dependencies. Stubs support state verification when we examine the output or final state of the system after execution. They don't fail the test, they simply supply predefined return values or stimulate specific condition. On the other hand, a mock is an object that contains pre-programmed expectations how the SUT should behave. Mocks are mainly used for behavior verification, checking that specific methods were called, how many times, and with what arguments. If the interactions don't match the expected collaboration pattern, the mock will fail the test. This makes mocks ideal for collaboration testing, interaction testing, and ensuring the SUT communicates correctly with its dependencies. In Fowler's words, stub focuses on inputs while mocks focus on interactions. Overview of test doubles. These include dummies, fake, stub, spy, and mock. In software testing, especially in unit testing and TDD, a test double is any object that replaces a real dependency to make tests faster, more isolated, and deterministic. Martin Fowler popularized the term, comparing them to stunt doubles, as talked about previously. Fowler identifies 5 main types of test doubles, as I listed. A dummy object is simply passed around because the method signature requires it, but it's never used. A stub provides predefined responses and is used to control indirect inputs, supporting state verification. A fake has a simplified but functional implementation, such as an in-memory repository or fake email service. A spy records details about how the SUT interacts with it, what methods were called, and with what arguments, and supports interaction tracking. And finally, a mock contains pre-programmed expectations and is used for behavior verification, failing the test if the expected interactions don't occur. Test doubles make unit tests stable, predictable, and aligned with modern clean architecture, dependency injection, and continuous integration practices. Factors improving testability. When talking about improving testability of software, there are 4 major characteristics that matter the most, such as controllability, observability, isolatability, and understandability. Controllability means we can fully control the inputs, configurations, states, dependencies of the system under the test, allowing us to create deterministic test environment and force edge cases. Observability means we can easily see the system's outputs, internal state transitions, error messages, logs, side effects. This makes failure diagnosable and debugging far more easier and efficient. Isolatability is the ability to test components independently by removing external dependencies by using mock stubs, fake spies, such as talked about before in the earlier slides. This supports clean, fast, reliable unit testing, and understandability refers to knowing how to keep the code simple, readable, clean, well structured, and the overall testability increases when the system also follows modular design, loose coupling, and single responsibility principles. With the implementation of all of these factors, you can have a very reliable and easy to test code and can run high quality automated tests that support TDD, CI/CD pipelines, and long-term software evolution. A good framework to follow for having good tests is TRIP, TRIP. And what it stands for is the T is for thorough, which means that it covers all of the relevant paths, edge cases, boundary conditions, and it makes sure that the tests, the error conditions, and the unusual states are all in check. Includes both positive and negative tests. The R in TRIP stands for repeatable. It means that it produces the same result every time on any machine under the same conditions, and there's no dependency on external systems like time, randomness, or environment. And it is critical for regression testing. The I stands for independent, just ensuring that the test is isolated for a unit test and does not depend on the outcome of another. Uses mocks, stubs, and fakes to isolate the system under test, SUT, and allows the test to be executed in any order without side effects. And the P stands for professional, keeping the test clean, readable, maintainable, following good naming conventions, clear assertions, descriptive test method names, and organized structure. TRIP is useful to ensure high quality, predictable, and trustworthy tests, supporting TDD, clean architecture, and scalable long-term development, reducing flaky tests, and improving the overall software maintainability. Here is a 5-question checklist you could use that every unit test must answer in order to go through with their unit test. What unit is being tested first, you need to figure out. And then what behaviors are expected and what is the actual output and what was the expected output. These are important questions to ask yourself while running these tests so you can compare. And finally, you need to know how can the failure be reproduced. You don't want the failures or the successes to be based on just randomness. You need to make sure that everything that you do during these tests can be reproduced under those same conditions again and again. So what is TDD, test-driven development? It is a development methodology where tests are where you ensure that features are designed with testability, clarity, and correctness from the start. It is strongly associated with having clean code refactoring and modular design. And the TDD cycle includes red-green refactor. The red is write a failing test, so define desired behavior through a test, or a test fails because the functionality doesn't exist yet. So a red is just when you fail a test, and a green is making the test pass when you implement the minimal amount of code needed to satisfy the test and focusing on correctness, not optimization. And refactor is improving the code by keeping it clean, restructure the implementation to remove duplication, improve the clarity, enhance the modularity, and the test must remain green throughout the refactoring process. The benefits of TDD include producing modular, loosely coupled, maintainable code, reduces bugs by validating behavior continuously, improving the design by forcing clear responsibility, and enabling safer, faster refactoring and debugging. Next is the benefits of TDD. The benefits go far beyond just writing tests first. One of the biggest advantages in TDD is that they improve software design by enforcing small, modular, and highly testable units. This can save companies tons of money by debugging at the unit scale and saving you much time later on. And because you write a test before the implementation, the code naturally just follows the single responsibility principle, has cleaner boundaries, and becomes easier to understand and maintain. TDD also results in naturally high test coverage because every new behavior is backed by a test before any code is written. This eliminates untested functionality and gives developers confidence in their system's behavior. Another major benefit is that TDD creates a strong regression safety net. The growing test suite ensures that when you add new features or refactoring existing code, you don't accidentally break previously working behavior. This leads to safer refactoring, faster debugging, fewer production defects. So overall, it encourages continuous improvement throughout the red-green refactor cycle. Developers constantly refine their code, remove duplication, enhance design quality while keeping their test green, making sure that TDD is a powerful practice for producing clean, maintainable, reliable software that can integrate smoothly with CI/CD pipelines. And finally, to end it off, here are some common unit testing mistakes that many people may make. The first one is testing too many behaviors in one test. The point of unit testing is to single out behaviors one by one and codes. So this can lead to confusing failures and unclear root causes. You may not be able to pinpoint where the bug is coming from. And it breaks the single assertion, single responsibility rule, and is hard to maintain, refactor, or diagnose. Another common mistake is using external dependencies, hitting real databases, APIs, file systems, or networks. This will slow the tests and cause non-deterministic behavior. And it violates the unit test isolation rule. So you do want to be using mocks, but another common mistake is overusing too many mocks. This would create a fragile and implementation coupled test. This would break during refactoring, even if the test might break, even if the behavior is correct. And it encourages focusing on interactions instead of outcomes. And another mistake is writing flaky tests, meaning that the test outcomes may depend on randomness or the order that they are run in, their external states, or even time that they are run. And it just destroys trust in the test suite and difficult to reproduce or debug. And some other common mistakes also include ignoring edge cases, which is crucial, and poor naming and structure, lack of cleanup or shared state. So it is important to keep all of these common mistakes in mind and not make any of them to conduct a proper unit test.